All right, College Trig, this is 8.7, the cross product. So far we have done these different things with our cross product. We have added vectors, we can subtract vectors, we can find the angle or theta in between two vectors. We can find the dot product of two vectors, which helps us determine if things are parallel or orthogonal. And we can work with vectors in space. So with cross products, what that's going to give us the ability to do is find vectors that are orthogonal to two vectors. We will only deal with cross products in space with 3 dimensions. So if you imagine you have vectors A and B, if you do A cross B, you get a vector that is perpendicular both to A and perpendicular to B, going off in the other direction by the right-hand rule. Notice that whenever you have two vectors, A and B, that it's always going to create a plane, and it doesn't matter. I can rotate this around, and we can see that we could have planes that are not necessarily just flat horizontal or vertical, and we'll always get a plane created by two vectors, as long as those two vectors are not parallel. So the big idea today is that the cross product creates a vector orthogonal to this plane, and that's going to be useful in many different contexts. So the cross product is most easily understood through the matrices. Okay, it's only used for 3D, and there's many applications here with the cross product. So some of this is review from college algebra. We're going to have to make sure you can find determinants. So to do the cross product, you're going to head ahead and set up the matrices, where you're going to have ijk as your column 1. And then you have the vector v. So if v was equal to a1i plus b1j plus c1k, A, B, and C goes there, and very similarly, W is there on row 2. So if you do V cross W, what you're going to have to do is you're going to have to find 3 different determinants. So the best way to do this is for the I component, you go ahead and cross out the rows and columns for I, and then you're left with this matrix, and you must find the determinant of that. So that's B1, C2, B2, C2, that's left there. So notice if we go ahead and look at the determinant from J, cross out the row and column that J's in, you're left with A1, A2 there, and C1, C2 here, and you have that J determinant. Similarly, we can do that same thing for K. So finding the determinant of K, we cross out the column, cross out the row, and we're left with this matrix, which is just there for K. Now remember, to find your determinant, you have this equation down here. So to do your determinant, so for the first part for I, it's B1 times C2 minus B2 times C1. And that's how we're going to have to find your determinant. Now remember, the second one, you're going to always have this minus sign there. You always got to subtract the J component through there on matrices. So with that, notice that it's A1 times C2 minus A2 times C1. And that's always going to be the factor that you need to subtract away the diagonals. And again, for K, you're going to do A1 times B2 minus A2 times B1. And that will be your cross product of V times W. Now remember that these are called determinants, so make sure you have this in your notes. Let's go ahead and look at an example. So to find the cross product of V cross W, I set up this matrix C, and I first look at I. So I'm just going to cross this out, and I'm going to get 3 times -1. So I get -3 minus -1 times 2 is -2. And then that is my I component. Now remember, it's always a minus sign here for my J. I'm going to cross out the rows and columns for J. So I do 2 times -1, and I get -2 minus -1 times -1 is a +1. And that is going to be my J component. Go over here, and you can just cross these out. You don't have to just, write them down, cross them out, and then take the erase them all the time. You can just lay your hand over it. But I think as we're starting off here, it's good practice. So then we're going to do 2 times 2 is going to be 4 minus -1 times 3, and we get -3. Close that out, and that's our K component. So then we're going to simplify. So I got -3 plus 2 is going to be -1I. Now I have -2, I get -3 inside my parentheses, minus a -3 is going to be plus 3J. And then the last piece is going to be 4 plus 3 is going to be plus 7K. So this is the vector that is orthogonal to these two vectors. These two vectors will create a plane, and from that plane we can find a vector that is orthogonal to it by the right-hand rule. You can see there's the work I'm writing out. You can just see that these are the determinants of I, J, and K, and finding the determinants of there, we get the same solution there. All right, so we have to talk about some properties that are unique to cross products because it's nothing we've been familiarized with before. So we want to know what happens when we do U cross U. So let's go ahead, just because it's the same vector, we don't have multiple A, B's, and C. We'll just call vector U A, I, B, J, and C, K. And let's go ahead and find the dot product of those two, or I'm sorry, the cross product of those two vectors. So I'm going to have, so if I set up my matrix, you have I, J, K, and I have A, B, C, A, B, C. I'm going to go ahead and pause this video here. Go ahead and calculate the cross product of vector U crossed by itself. So looking at the algebra from this, you can see that we get the same thing. So something minus itself, we get 0, I minus 0, J plus 0, K, which is our 0 vector, which should make sense because if we have one single vector and it's itself, we don't get a plane defined, so we can't find a vector orthogonal to it. So vector crossed by itself, we get the 0 vector. Another property that's, so remember, these are some of the properties that we should understand, that if we do vector crossed by itself, we get 0. If we do a vector in the opposite way, so we do U cross V equals -V cross U. So if you do it the other way, it goes off into the other opposite direction. If you look at the picture from here, notice A cross B, we got the vector C going up. If we did B cross A, we got the vector D going down. It's the same vector, just in opposite directions. So that is an example of this product here, that if you do it in the opposite direction, it's just a vector negatively. If you want to multiply it by a scalar, remember alpha in vectors is typically a scalar, just a number. You can do A times U crossed with V, and U that's equal to u times a crossed with v. Either way, you can do any one of those three equations. If we want to do u cross v plus w, that's also the same as u cross v plus u cross w. Well, the problem with this is cross products take a while. That means we're going to have to do 6 determinants, 3 each. If we do it this way, we can just add u plus v, and let's say v plus w is the vector y. So then we just have u cross y, and we only have to do 1 cross product and 3 determinants. Make sure when you do determinants, you keep your work organized. Make sure you show all your work, because it's very easy with that to get mistakes. And if you show all your work, I can give you as much points as possible, even though you might got off by a negative sign. The final thing I want to look at is, remember, two vectors are orthogonal or perpendicular if their dot products are 0. So we want to go ahead and look at the proof of this and why this could be. So we have vector u and we have vector v, and we go ahead and we want to take the cross product, and we want to show that the cross product dotted with the other vector is equal to 0, because u cross v should be perpendicular to u. So if we take the cross products, I'm going to go ahead and we need to set up the matrices that we have I, J, K. We have A1, B1, C1, A2, B2, C2. I'm going to go ahead and do the algebra here, pause it, and check back in here. Why don't you try the same? So now that you can see, we took our cross product and we get this vector here. And remember, if it's a proof, we should have a generic form. We don't have numbers, and that's one thing that I think some of us struggle with a proof, is we have to be generic and use variables and numbers, and just showing a single example is no way near a proof. There's lots of errors in your logic if you believe one example is proof that something is true. So what we want to do here is, now that we have u cross v, we want to find the dot product. So remember, the dot product, we just multiply our components together and add them. So if I do it with u, I could do it with v because it should be perpendicular to both of them. But if I do a1 times the I component of my cross product, I get b1c2 minus b2c1 I minus b1 times a1c2 minus a2c1. That's my j component. And then I'm going to add that to the dot product of, and my apologies, it's a dot product, so we're just adding these parameters together. And it's not going to be a resulting vector. And then we do plus C1 times A1 B2 minus A2 B1. Go ahead and collect your like terms and see what you get. So after distributing and finding the dot product there, notice I went ahead and underlined the vectors that were opposites. So A1, B1, C2 is the same thing as an opposite with the negative sign of B1, A1, C2, because multiplication, the order doesn't matter. We have a C2, we have an A1, and we have a B1, the same thing as this vector. So all the vectors underlined, the opposite vector are underlined in the same color. So because they all cancel out, we get a dot product of 0. Therefore, we know they're perpendicular. All right, that's going to conclude our notes tonight. Make sure you come with questions tomorrow, and we'll do part 2 of this tomorrow night.